Okay, before y'all leave, y'all pick up the naming acid practice. I'll actually set them on this table. And Alright, so I sent an email out to the 11 o'clock class because they're not actually meeting today. But I did extend your mastering homework for chapter 8 to Wednesday. So it's not due tomorrow night. Instead, it's due Wednesday. Okay. Wednesday, we left off talking about acids. We named them. So we said that acids were substances that produced a hydrogen ion in water. Bases were substances that produced an OH in water. I didn't tell you that, but that's what a base is. An example of a base is sodium hydroxide. So when it is in water, it's going to break apart into my sodium ion and my hydroxide ion. With acids, we had to talk about naming. With bases, we don't have to do that because you already know how to name them. It's just whatever metal you have. So here I have sodium, and then the word hydroxide because this is the hydroxide ion. There's nothing special about it.
Just regular name?
Yep. So, strong bases contain the hydroxide ion in their formula. There are several weak bases, but I'm only going to give you one. It's ammonia.
You said that strong bases contain that in their name?
Yeah. So, because we're kind of running out of time, we're only going to focus on strong acids and strong bases when it comes to writing equations. But I kind of want to introduce some weak, both acids and bases. I just won't use them in reaction problems. So before I move on, let me show you how NH3 acts as a base. So if I were to put NH3 in water, because it is weak, I use this double arrow because it doesn't completely dissociate. I mentioned that when we first started talking about this chapter. So it doesn't dissociate 100%. So what that means is when this solution reaches equilibrium, I will have some base that is broken apart and I will have some that remained intact. So what this does, NH4 actually takes a hydrogen from water to form the ammonium ion, and so it leaves water as just OH. So that's how NH3 is a base, even though it doesn't have OH in its formula. Okay, I want to add more to our acids. There are 6 strong acids. Those are your 6 strong acids. I'm going to put an asterisk by H2SO4. So this is like total. Some people will argue and say that there are a few more strong acids. They really aren't strong. I mean, they're stronger than weaker acids, but they're not strong by definition. So all of these acids dissociate 100% when you dissolve them in water. Sulfuric acid is weird. It is what we call a diprotic acid. What that means, di means 2. Protic refers to protons, which hydrogen plus is just a proton because you removed its electron. So that means it has 2 protons or 2 hydrogens to give up when it's dissolved in water. When it does that, it does it in a stepwise manner. Okay, so I start with H2SO4. I put that in water. It gives up 1 hydrogen but leaves the other. Okay, so this first ionization just means I broke it down into its ions. This first ionization, H2SO4 is acting as a strong acid. When I take HSO4 minus, I will get rid of the other hydrogen. But this ionization, HSO4 minus, is actually acting as a weak acid. The reason it is because it's already negative. So it doesn't want to give up one of its positives to make it more negative. So it's resistant to do that. just to give you some examples. There are a lot of weak acids, but HF is a weak acid, hydrofluoric acid. HCN, hydrocyanic acid. And then another polyprotic acid would be phosphoric acid. We call that a triprotic acid because it has 3 hydrogens to give up. So just because it's a weak acid does not mean that it's any less harmful. Okay? Weak in our terms just means it does not dissociate 100% in water. Hydrofluoric acid is still very dangerous. Like if you have hydrofluoric acid in the building, you have to have its antidote for safety measures. Because if it burns you, it's going to burn you good. Okay. So let's talk then about acid-base reactions. It goes there. Alright, when an acid and base react with one another, it's called a neutralization reaction. So, we're going to react an acid with a base. We are going to produce a salt, which is an ionic compound in water. Okay, so with our salt, it's going to be an ionic compound. And when we predict our products, always check the solubility of your salt. Okay, sometimes it will form a solid. Not very often, but sometimes. So always check that. Alright, so let's look at an example. So I have HCl and NaOH. We're going to follow the same steps as we did with precipitation reactions. We're just forming new products. Okay, so let's break both of these down into their corresponding ions. I'd have sodium plus 1, OH minus, then I'd have H plus, Cl minus. with your acid-base reactions, your H plus and your OH go together because that is what is forming the water. Okay, so then the other two ions are forming your salt. Again, always check your solubility on your salt. NaCl is soluble, so it's aqueous. Okay, so those are my two products. I'm going to go over here, write them in. And then I would balance it if I needed to. It's already balanced. Okay, so that's just me predicting the products. Now let's write the complete and the net ionic. Alright, so for your complete ionic, you're breaking everything down that is aqueous and a strong electrolyte. So this is a strong base, so it breaks down. This is a strong acid, so it breaks down. Okay, then I go to the other side. Since my salt was soluble, it breaks down. Do I break water down or leave it together? Leave it together because it has an L behind it. That means it's a pure liquid. You don't break apart pure solids, liquids, or gases. Alright, who are my spectators? I'm just going to cross them out. Bring everything else down. And my net ionic is just the formation of water.
Since acids and bases always produce salt and water, will that always be our net ionic?
As long as both of your acids and bases are strong, then yes. Let's do an example with a weak acid, just in case you encounter that on mastering. Alright, so let's react hydrocyanic acid, HCN, with lithium hydroxide. So it's a weak acid with a strong base. Because I have a weak species, instead of using the one arrow, I have to use the double arrow. Okay, now proceed as normal for now. So just break apart those two into their ions. Okay, I'm going to form water, of course, and lithium cyanide. So I have LiCN plus H2O. Leave anything with lithium is always soluble. Okay, we good there? Nothing new just yet. Yes.
So when you give us the 6 strong acids, we use the one-way reaction symbol, but anything else is substituting, even like the intermediate acids like
Yep. Okay. Alright, this is where things are different. When you go to write your complete ionic and your net ionic. Because HCN is a weak acid, I don't break it up. So I leave it as HCN. I break up my strong base because it's strong. Okay, and I do the same thing as I would normally do on my product side. Break up my soluble salt. Leave my water together. It is a pure liquid. Alright, so here I only have one spectator. Who is it? Yes. I'm going to cross it out. Everything else I'm going to bring down. Okay, so that's what my net ionic equation looks like. I have that weak acid, and then this is called the conjugate base of the acid. So we haven't talked about that, but those remain in my net ionic equation. Any questions? Alright, let me give you one to do real quick, and we'll do something else. Alright, predict my products, then write your complete ionic and your net ionic for this equation. here is the answer. When you get to the net ionic, if you want to reduce all these coefficients down to 1, you can, or you can leave them like that, doesn't matter.
Did you simplify when you got there, or were you?
You could.
I do think the mastering helps off.
It shouldn't. If you'll send me the prop, or go back and look, and then if it did, send me the prop. Alright, we good with acid base? Pretty simple. If you look at the PowerPoint I posted, there's more examples in there that you can go through and do if you need extra practice. But now we get to switch to some math for a brief moment. Alright, if you have to do the makeup lab, we're doing experiment 10, and it is an acid-base titration. So, in acid-base titration, let me define the word titration first. If you've ever done a titration before, you know it's very tedious. It's where you have a substance in a solution and you know its concentration. You react it with a substance that you don't know its concentration, and you use solution stoichiometry to determine the concentration. Normally, we do this if we want to know the exact concentration. Like instead of saying, oh, that's a 1 molar concentration, no. We can figure out that it's like a 0.9987 molar concentration. So it's very exact. So the titrant, that's normally the substance whose concentration you know, is added slowly to a flask that you don't know the concentration of in an instrument called a burette. So burettes are very, very accurate when delivering volume. Most of like your graduated cylinders in lab, there's anywhere from a 1 mil to a 5 mil error. With a burette, it's like a 0.001 mil margin of error. So it's in a very exact form or exact instrument to use. So how do I know how much to add? Good question. So we use a chemical indicator. We put it in the flask. When that indicator changes colors, that tells me that I've reached the end point of the reaction. For an acid-base reaction, all right, so for an acid-base reaction, the end point is reached when the number of moles of the H plus ions equal the number of moles of the OH ions. This is also called the equivalence point. So you choose an indicator based on the pH range that you're looking for. That's how it changes colors. Okay, so how do we do the math? So in the beginning of this chapter, I think we only did one example, and I called it solution stoichiometry. We're going to do the exact same thing with acid-base titrations, okay? So let's look at an example. Alright, so the first thing you have to do with acid-base titrations, normally the equation is not given to you. So you've got to write the equation and balance it before you can ever start working with the problem. Let's do that for this. So I'm reacting H2SO4 with KOH. This probably wasn't the best example to start with. Alright, so the products I'm going to form from H2SO4 is K2SO4 and water. If I give you H2SO4 as your acid, I'll give you the equation, okay? Because I know what you're probably thinking. But a second ago you told us that it didn't do that like that. It doesn't, but it's very important that it's balanced. That's the only thing that really matters here. Alright, so these are my products. I need a 2 right here and a 2 right here. Right? Alright, so then I'm going to take my volume and my molarities and I'm going to put them under the corresponding reactants. So we don't know the molarity of the H2SO4. We do know that we're going to use 20 milliliters of it. Then we know that the KOH is 0.158 molarity, and we're going to use 22.87 milliliters. Alright, so this is where we have to like set up a bridge. We have to, the only way we can relate these two reactants is through the mole to mole ratio. You cannot use M1V1 here. It won't work. Okay. So I'm going to show you how to do it, and then I might show you the shortcut if I have time. Let's start with the volume of the base, since we know both its volume and its molarity. Okay. 22.87 milliliters KOH. I need to convert this to moles of KOH so that I can relate it back to H2SO4. I can do that using the molarity, but this needs to be in what unit? Yeah, so let's go ahead and do that. So 1,000 milliliters, 1 liter. Okay, now I can use my molarity. So I can use molarity as a conversion factor because by definition, molarity is moles of your solute over liters of solution. So that's going to cancel all that, and I'll be left with moles of KOH. Now I can use the mole to mole ratio. For every 2 moles of KOH, I need 1 mole of H2SO4. So if I can stop there and solve for moles of H2SO4, I can take that in this volume and find its molarity. So 0.00181 I'll do, since this is not my final answer. Okay. So now if I take that moles in this volume, I can find molarity. So it'd be 0.00181 moles. This needs to be, this 20 mils need to be in what? Yes, so that I'm just going to do real quick. I'm just going to move my decimal 3 places to the left. Get 0.0903. Does that make sense how I did that? Okay. So Monday I'll do some more examples and I'll show you one way you could work this a different way. I'll do that on Monday. Okay? I hope to finish chapter 8 on Monday. We will not get very far in chapter 9, but we will get some of it. Y'all have a good weekend. Don't forget to pick up the naming acid practice.